So let's recall from our previous video that given certain conditions that I'm not going to dive too heavily into right at this moment, but we basically looked at how as n increases or p is relatively close to 0.5, our binomial distribution looks very similar to a normal distribution. And we talked about last time how the mean of that normal distribution would be found by taking n and multiplying by p, and the standard deviation would be equal to the square root of the product of n times p times 1 minus p. The symbol mu, the lowercase Greek letter mu, is used to represent the mean of a population, and the lowercase Greek letter sigma is used to represent the standard deviation of a population. So we have a scenario here similar to the previous scenario, just for the sake of consistency. We have 150 fish, and we know that there's a 60% chance that any one fish is female. So the first challenge is, using binomial CDF, find the probability that 80 or fewer are female. So this is just like we've done with binomial distributions, just a review of that. So I know that in order to do this, I'm going to need binomial CDF. And my first entry is my number of trials, which is 150. My probability is 0.6. And the upper bound of what I want to find the probability of is 80. And I know that this will find the probability for me for up to 80 of the fish being female. So I'm going to get out my calculator here. And I need to go again into my distribution menu. I'm going to scroll down to binomial CDF. Right, and I have some previous information in here from the previous time I used this. I'm going to change my x value to 80, and I'm going to paste it. And it tells me that the probability that this would occur, according to binomial CDF, is about 0.057, or a little less than 6%. So about 0.057. All right. Now, the second problem says, using the normal approximation, find the approximate probability that fewer than 80 are female. So now we're treating it like a normal distribution, right? So in this case, I'm going to need normal CDF. And recall that normal CDF first takes in the lower and upper bounds. So my lower bound here just has to be a pretty low number. It doesn't, as long as you're low enough. I had my students use negative E99, which works pretty well because that's about as low as the calculator can go. The upper bound in this case is 80. The mean is n times p, which we saw last time is 0.6 times 150, or 90. And the standard deviation is the square root of 150 times 0.6 times 0.4, which we saw last time is exactly 6. So putting this into the calculator, going to get my calculator out again. So I'm going to go back into distribution menu. Now I want normal CDF. And conveniently, it already has negative 1E99 as my lower limit. My upper limit is going to be 80. My mean is going to be 90. And my standard deviation is going to be 6. So this answer should be close to what we got for binomial CDF, because as we saw on the Desmos activity, in this case with a p of 0.6 and an n of 150, the normal curve looks pretty close to the binomial distribution. And it is pretty close. So the normal CDF gives us a little less than 5%. It's about a 1% difference total between the two methods of finding this probability. So this one came out to about 0.047. So very close. So you could see that in practical terms, once upon a time, if this was very hard for them to do by hand, this got them pretty close for most things. So that's another example of how we would use the normal CDF to approximate a binomial CDF problem. Now, one thing I also want to address really quickly here, because this has come up with a few students, is that notice that my language here is I said 80 or fewer, and in this one I said fewer than 80. But in both cases, we set the upper bound to 80. So if this were a binomial CDF problem, and we said fewer than 80, we would want to set our upper bound to 79. Why did I not do that here, even though my language is fewer than 80? And the reason is because a normal distribution is a continuous distribution, which means that essentially saying the probability of fewer than 80 or up to 80 or 80 or fewer is actually really saying the same thing. And I know that that seems counterintuitive, but it's a property of what we call continuous distributions. Basically, the thing you have to remember is that if you're using a normal curve, and you have an upper or lower bound, it doesn't matter if that bound's included. You end up always putting it in the CDF anyway. So essentially, normal curves are simpler that way. You don't have to worry about whether or not the language includes the boundary. You're always just going to put it in. The technical reasons why that works would be covered in a more technical statistics class, but that's what you need to know for right now. If you're using a normal curve, you always put in the boundary, whether it says fewer than, or at most or at least, you always include the boundaries. So now let's move on to a slightly more hypothetical scenario. A lot of times in statistics, when we're looking at proportions of things occurring in populations, we don't care nearly as much about how many things we're sampling as much as we care about the proportion itself. For example, if I told you that a survey said that 70% of all Americans think that vanilla ice cream is the best flavor, which vanilla ice cream does tend to be the most popular flavor, you as a consumer would probably care less about how many people I actually surveyed to get that information than you would about the actual proportion. Even though as a statistician, you would certainly care how many people I sampled, at the end of the day, people care more about the proportion itself. That means more to them because now they're thinking that that number represents the entire population. Whether or not that's really true, that depends on a lot of other factors. So typically, when we're looking at population proportions, we care much more about the proportion itself than we do how many people actually got sampled or how many things got sampled to find that proportion. So it kind of makes sense to be able to have a distribution that focuses really on the proportion itself and not really, and making that really the central point, literally. So let's go back to our fish and let's do a hypothetical scenario. So let's say that, we're going out on our deep water expedition. There's my beautiful ocean, and I've got my boat. Put a porthole there. So there's my beautiful boat. And this boat is actually going out and it's sampling some deep water fish. And we found, got some really big tails on these fish, right? So it's actually going to sample the fish, and it's going to sample a certain amount of fish, and it's going to record down how many are male and how many are female. Now, again, we're assuming that we know that in this particular type of fish, 60% of all specimens are female. So let's say we start by sampling 30 fish at a time and recording down what proportion of them ended up being female. So now we would expect that number to be around 60%, but we know it doesn't have to be. But we expect it to be close. It's possible we get all males in our 30 fish or all females, but it's unlikely. So we do this, we sample these 30 fish and we get the proportion. The question is, if we do this many, many times, keep going out and sampling 30 fish at a time because we really have nothing better to do and we just really love sampling these fish, and we recorded down the proportion of females every time we went out and sampled 30 fish, what would that distribution of proportions end up looking like? That's what we're talking about here today. So to simulate this, I actually have in my little virtual TI-84, I actually made a program that will do this for me. I called it PropSamp because we are sampling our proportions. So I'm going to make PropSamp happen. Okay, so the first thing it wants is what's the population proportion that I'm talking about, and for our fish, it's 60% are females. We're still going with the females. How many? The N here is going to represent how many fish we're sampling at a time. So I'm going to say we're sampling 30 fish at a time, and it wants to know how many times are we going to sample these 30 fish. So like how many days in a row are we going to go out and get these 30 fish and record down the proportion that are female. And we're going to go out there 50 times. And the calculator should find these 30 fish, find what proportion are female, do that 50 times, and it should store the information in L2. So if I go into my calculator's list and I look at L2, I can see that L2 has all the proportions of fish that were female from each of the 50 trials. L1 stored whether or not the fish was female, so you don't have to worry about that. So what does this distribution of proportions actually look like? So easiest way we could kind of think about that is, what would we expect like the center of the distribution to be about? What would we expect the middle of all these proportions to end up being? So as you saw, a lot of them were 0.6, 0.567, 0.6, 0.667, 0.667, 0.5667, 0.6. So it looks like a lot of them are clustered around 0.6. There's a 0.5, there's a 0.4, so that's a little on the low side. But we said that's possible. We go out there and we get a large number of males or females, exclusive. But my calculator can actually tell me what the mean of that list is. So I could say, what is the actual average proportion over the 50 trials? And according to my calculator, the average proportion is 0.591, so just barely below 0.6. So that's really close to 0.6. Now that's kind of what we should expect. If most of the proportions are going to be around 0.6 and it's less likely that it's further away, we would kind of expect them to cluster around 0.6. Now another thing I'm going to look at is the standard deviation, which tells us how spread out are these proportions. So, wrong menu. I'll go into math here, and I've got my StinDiv right there. So StinDiv. So my standard deviation in this case is about 0.078. So that gives me an idea of how far spread out these proportions were. So if I thought of it like a normal curve, although I don't really know at this point if it is a normal curve, we'll talk about that in a bit. So that means that about 68% of all of my proportions should fall within 8% about of 60%. So about from like 52 to 68 should be most of the proportions that we found. So let's consider the situation where we're going to do the same thing. We're going to go out there and we're going to sample these fish, and it's the same fish, so the probability that there's a female is 60%. But here's the deal. We're not going to sample 30 fish at a time. We're interested to see what happens if we sample, let's say, 100 fish at a time. And we're going to do that 50 times. So I'm going to sample 100 fish at a time, and we're going to do that 50 times. So what I want you to think about before we do this is, should anything change in the results that we get if we increase the number of fish that we sample at a time from 30 to 100? All right, our calculator's finished working. So it again stored all of my proportions in L2. So I can take a look at them here. And again, they look very clustered around 0.6. But as I scroll through, I'm seeing like fewer 0.4s. Like there's nothing, I'm not seeing a whole lot of numbers that are further away from 0.6. But I want to actually confirm if that's what's happening. So I'm going to quit, and once again I'm going to ask my calculator to actually compute what the average proportion was that we found of our 50 days going out and getting 100 fish at a time. And wow, all right, so that's very close to 0.6, even closer than the last one we got. So let's take a look at the standard deviation. Let's see what happened there. So I can go on to math. And I'm going to check out the standard deviation of my set here. So if you recall, it was about 0.079 or close to 0.8 last time. Look what happened here. It went down. Right? So now it's 0.0459. So that would mean, again, assuming this would look roughly normal, which we haven't really established yet, that would mean that about 68% of all my proportions here fell within 4.5% of 60%. So like from about 55.5 to 64.5% would be most of my proportions. So that's not only is it all still close to 0.6 in terms of centering, it's a lot closer to that center. So now we're going to talk about why is this actually happening, what's going on. We saw that in our fish case that each time we went out and we sampled all of these fish, in each case our proportions seem to cluster around 0.6, or the overall proportion of females we know is for this population. But in the 100 fish case, the standard deviation, how far apart those proportions were spread, was smaller than the 30 fish case. So why should this actually occur? Well, let's recall that previously, when we had a set number of fish that we were sampling, the expected number of fish that were female was n times p, or in this case the 0.6 times the 150. Well, in this case, I don't really care about n. So what I'm really doing is taking this and dividing it out. So by dividing by how many fish we sampled, we get a new mean of this distribution of just p. So in this case, it makes sense that our distribution should actually center around whatever our population proportion is. So the mean in each case was very close to 0.6, because in the actual world, it would have been 0.6. What about our standard deviation? So before, it looked like this. It was n times p times 1 minus p. But again, because I don't care how many fish I'm sampling, I want to divide it out. But that's going to do something interesting here. I'm just going to do the math very quickly. If this part doesn't capture your fancy, I won't take offense. You can just skip ahead to the conclusion, but I want to show this. So the easiest way to show what would happen here is if I put everything under the square root sign, the n is going to become an n squared. And then under the square root, I have an n and an n squared. So one n is going to divide out numerator and denominator, and I'm left with the square root of no more n in the numerator, just p times 1 minus p, and the denominator inside the square root is just n. So what does that actually mean? It means that as n increases, as the number of fish I'm sampling every day goes up, in theory, the standard deviation of those proportions should go down. So that should make sense intuitively. The more fish we're sampling every day, the more those proportions should cluster around whatever the population's proportion is, which is 0.6. If I'm getting more and more fish, I expect closer and closer results to the population proportion. So I would expect it to be much harder for any one proportion to get far away from what the population proportion is. So some people have said in class, like when something like this happens, so in other words, bigger samples means more accurate information. And yeah, that's one of the big takeaways from stats. By sampling more fish, our proportions were, on average, closer to what the actual population proportion is. And that's what we sort of expect to happen. So to summarize what we know for a sampling distribution for a population proportion, we know that these distributions are indeed roughly normal. And we know that the mean of these distributions is exactly whatever the population proportion is, which we're going to call p. And the standard deviation of these distributions is the square root of p times 1 minus p all over n, whatever our sample size is when we're taking the proportions. We can use this information to solve problems about population proportions. So let's actually use this idea to answer a hypothetical question. So let's say that we know that 72% of all Brookfield residents prefer Bello over La Familia. Again, we're given that mystical information, and I have no idea if that's actually true. I just made that up. So if we survey a random sample of 40 residents, what is the probability that 65% or less prefer Bello over La Familia? So we're going to use our sampling distribution for a proportion in order to answer this question. But before we do that, I like to establish what the mean and standard deviation should be of this proportion. So I can see that 72% of all Brookfield residents prefer Bello over La Familia. That's the population proportion. So I know that that's actually the mean of my of my normal distribution, so I know it's going to be about 0.72. All right. We're also told that we're sampling, in this case, 40 residents, which I need for my standard deviation. Note that doesn't affect the mean. I always expect the mean to fall around the population proportion. It should be 0.72 in this case. But that's going to affect how spread out my distribution of proportions is. So I'm going to need my calculator to do that. So I'm going to bring up my TI here, and I need to do the square root of 0.72 times, and I need 1 minus p, which is 0.28, and that has to also be divided by 40, still in the square root. So according to my calculator, the standard deviation of this distribution should be about 0.07099. I'm going to run that to 0.071 because that looks pretty close to 0.071. So let's make a note here. 0.071. If I were writing on the board, I would actually use the mu and sigma, but again, my handwriting's pretty bad on this, so I'm going to leave it at that. So how do I use this information to answer this question? Well, I want 65% or less. So I imagine having my normal curve here. The mean is around 0.72. So 0.65 is like over here somewhere, and I want everything up to that point. So I'm going to need to use normal CDF. And again, I need a big lower bound. My upper bound is 0.65. My mean here is 0.72, and my standard deviation is 0.071. Once I have that, I can use my calculator to get the answer, so I will. So again, going into my distribution menu, you should be very used to going into this menu by now. Normal CDF. It already puts negative V99, which is great. I'm going to do 0.65, and my mean is 0.72, and my standard deviation is 0.071. Paste. And it's about 0.162. So the probability that this would occur in our sample of 40 residents is around 16%, 16.2%. So our answer is 0.162. All right. So now that kind of makes sense, because notice my standard deviation here is about 7%. So it makes sense that 65% is about one standard deviation below the mean. And if we recall from our normal distributions, the area below one standard deviation below the mean is about 16%. So this makes sense. So let's look at the next question. What would change if we surveyed a random sample of 100 residents? Well, our n is increasing. Our p is the same, right? So the only thing that's going to change here is our standard deviation. And what's going to specifically change is the standard deviation should get smaller. And when it gets smaller, our distribution should become less spread out around the mean. So I would imagine in that case that basically what would happen is our curve would go from that to something like closer, so that 0.65, if I could try to draw this, that 0.65 is probably going to represent a much smaller area on this new curve than it did on the previous curve. In other words, the probability should go down. But let's actually do the math, because that's what we're here to do. I'm going to get rid of this guy because I don't need him. Let's make this go away. Oh, made too much go away. There we go. And let's actually just do the math here. So I need a new standard deviation because my n changed. So I'm going to put in my new information, 0.72 times 0.28. Since p didn't change, the numerator here doesn't change, but my n changed, it went up to 100. So this should be a smaller number, and it is. My new standard deviation is 0.04489, so I'm going to say 0.045 to keep rounding to the same place as I did before. So I'm just going to make a note here that we have a new standard deviation of 0.045. Other than that, the problem solving method here is essentially the same. It's a normal CDF problem. My lower bound is still negative V99. My upper bound is still 0.65. That hasn't changed. My P hasn't changed. It's 0.72. But my standard deviation has. It's 0.045. So I would expect this to be a smaller percentage. Let's actually use our calculators and get the result here. So my normal CDF, and this is the only thing that has to change, 0.045. Paste that. And our percentage went from 16.2% to just about 6%. So our new probability is about 0.06. So note the change here. By increasing the sample size, the probability we would get 65% or less preferring Bellow went from about 16% to only about 6%. And that should make sense because since we're sampling more people, the proportion that we would get should be closer to the population of 72%. Since 65% or fewer is kind of away from that, I would expect that sampling more people, it'd be less likely that that would occur. All right. So big takeaways here is that what's nice about doing sample proportion problems this way is when the number of people or things or whatever it is that we're sampling changes, the only thing that changes is our standard deviation. It doesn't change the mean. The mean stays at the population proportion, whatever that happens to be. So I hope you have enjoyed this and that it makes sense. And we will see you guys next time.